Welcome back to another explainer. Today, we are unpacking the brilliant engineering that keeps our computers from just totally crashing under the weight of, well, us, human interaction. We type, we click, we plug things in all day long, but under the hood, managing that absolute chaos takes some serious architectural genius.
So how does a CPU handle millions of calculations while juggling keyboards, displays, and these sudden interruptions without missing a beat? Well, let's imagine the CPU as this incredibly fast, incredibly smart, but completely overwhelmed executive. This executive desperately needs specialized assistance to handle the unpredictable chaos of the outside world. I mean, if the CPU had to stop everything it was doing every single time you pressed a key, nothing would ever get done.
All right, here's our roadmap for today. We'll start with the CPU's specialized hardware assistance, look at managing interrupts with the 8259, data transfer with the 8251, human input with the 8279, and then wrap up by diving into the architecture and pin configurations of these chips.
Section 1. CPU's specialized hardware assistance. Delegating the chaos.
Section 2. Managing interrupts. 8259 PIC.
Right, so to avoid a total processing bottleneck, the CPU offloads specific types of chaos to dedicated large-scale integration, or LSI chips. Think of our first assistant, the 8259 Programmable Interrupt Controller. As the ultimate executive receptionist, its entire job is prioritizing urgent phone calls for the boss. And what's absolutely brilliant here is how the 8259 automatically resolves priorities without needing any extra hardware. It natively handles 8 levels of priority interrupts, but if you're running a massive system, you can actually cascade these chips in a master-slave setup to manage up to 64 different levels of interruption. It's also super flexible, operating in fixed or rotating priority modes. Plus, if the CPU's in the middle of something absolutely critical, software can just temporarily mask those interrupts, basically putting up a Do Not Disturb sign.
Section 3. Data transfer. 8251 USART.
Moving on to our second assistant, the 8251 Universal Synchronous Asynchronous Receiver Transmitter. It's a bit of a mouthful, but it essentially acts as the CPU's dedicated translator and shipping department for external data. And this brings up the fundamental dilemma of data transfer. You basically have two choices. Do you send information sequentially down a single lane, which is serial transfer, or do you blast it all at once across multiple parallel lanes?
It all comes down to a crucial trade-off. Parallel transfer is blazingly fast because it moves 8 or 16 bits of data at the exact same time. But the catch? It needs up to 17 physical wires connected between the sender and receiver. That is just literally impossible to manage over long distances. Serial data transfer, on the flip side, moves just 1 bit at a time. Yeah, it's slower, but because it only needs 2 lines, one for data and one for ground, it's the perfect, elegant solution for long-distance communication. And the 8251 manages these protocols flawlessly.
Section 4. Human input. 8279 PKDC. Now we meet the assistant tasked with the agonizingly slow and messy job of talking to us humans. The 8279 is an absolute powerhouse. It's a programmable device that handles display operations and keyboard inputs at the exact same time. It's got 3 distinct input modes: scanned keyboard, scan sensor, and strobed input. But the real magic here is the 8-byte FIFO, first in, first out memory buffer. It literally remembers your keystrokes, holding on to them safely even if the main CPU is busy doing something else. And it's smart too. It has 2-key lockout and N-key rollover with built-in contact debounce. That means if you accidentally mash multiple keys at once, it doesn't just panic and crash.
Section 5. Architecture of the 8279.
Okay, let's pop the hood. Now, the full architecture of the 8279 might look a bit intimidating at first glance, but it's actually a beautifully logical flow of information. You've got control units, memory buffers, and scanning counters all working perfectly in sync. We're going to isolate a few of these specific blocks to see exactly how data journeys through the chip.
Let's start with the data buffer. This is how we build our connection to the CPU. The DB0 through DB7 pins form a 3-state bidirectional data bus. Basically, it's the main highway where data and command words travel to and from the CPU. But you don't want traffic collisions, right? So, the flow is strictly controlled by the I/O control block using the read and write pins. These pins explicitly dictate whether the buffer is currently taking data in from the CPU or sending data out to it.
Next up is the dedicated 16-byte display RAM, which is just amazing. Think about older displays. They have to be constantly refreshed just to keep the text visible on the screen. Instead of forcing the main CPU to waste valuable processing cycles doing that repetitive chore, the 8279 handles the whole shebang internally. The CPU just writes the data into this display RAM once, and the chip's internal address registers automatically update to accept the next entry. It handles the continuous display refresh entirely on its own.
All right, let's talk about the keyboard debounce and control block. Because human fingers are inherently messy, pressing a physical key actually creates a bouncing, stuttering electrical signal. If the CPU read that raw noise, it might think you pressed the spacebar 5 times instead of once. The keyboard debounce logic cleans up that physical noise, encoding a single, clean value and tucking it safely into the FIFO. At the exact same time, the return lines RL0 through RL7 are continuously scanning row by row, just waiting to latch on to those key closures.
Section 6. Signals and pin configurations.
To really grasp this hardware, we need to step back from the abstract logic and look at the actual physical pins connecting the 8279 to the motherboard. Every single pin has a highly specific job. You've got your standard power and ground lines, VCC and VSS. There's a CLK pin generating internal timing and a reset pin to clear the board. But I really want you to pay special attention to the IRQ pin. This is literally the alarm bell. The interrupt request line goes high to interrupt the CPU only when there's actually valid data waiting in the FIFO RAM. Once the CPU reads that data, the pin goes low again. It is the ultimate don't call us, we'll call you system for the microprocessor.
Finally, let's look at where the physical world meets the digital world. The scan lines, SL0 to SL3, are constantly scanning the keyboard matrix. Meanwhile, the return lines, RL0 to RL7, are normally kept high. But the moment you press a key down, you are physically bridging the gap between the scan lines and the return lines, pulling that normally high signal down to a low state. That specific grid coordinate is what triggers the whole process. There are even dedicated pins like Shift to tell if you're holding a modifier key, and BD, or blank display, which turns the screen off for just a fraction of a second during digit switching to keep the visuals looking super crisp.
Looking at the intricate, precise engineering of these LSI chips, it really leaves us with an incredible thought. We've just mapped out the literal physical pathways of how a CPU manages the absolute chaos of inputs, outputs, and interrupts. So next time you plug in a wireless USB device or just tap a touchscreen, ask yourself, how did these elegant legacy methods of delegating chaos pave the way for the invisible, seamless modern technology we just take for granted every single day? Thanks for exploring this with us, and keep asking the big questions.